Hi everyone. Today we have the pleasure to have Laura Bernard from Lux. So Lux is the successor of Lux in Meudon, if you knew about it already. But I let Laura explain if you want more details. But so today Laura is going to talk to us about curvature dependence of gravitational wave tests from theory to observation. So if you have any questions, feel free to ask during the talk. They will just have some time afterwards. Please, Laura, the floor is yours.
Thank you. Thank you very much for the invitation. I apologize.
If you want to, you can write it somewhere. If you click anything, then yeah.
Okay. So I open it. And yes, you have a nice picture of the with this. Let me start. So I start by normal things. So you know that we have detected many gravitational waves. So this is a proof three where now we are detecting with something like 1 element per day, let's say, or like 1 element per day, let's say. And so we need to be able to, so one key ingredient to be able to do detection of our gravitational wave detecting. And so that's why I got it. And so in the following, I won't answer all these questions, but I will. So these are the questions that motivate, let's say, more. So the first question is why do we need to have a precise waveform? I already more or less said that we want to detect that. So why also do we need to use different modeling techniques, so numerical relativity, but also analytical methods, and finally, because I will speak about direct gravity, why do we want to go beyond PR? Because it's moving very well also. So let's start the first question. As I already said, like the signal of gravitational wave is very small, so to be able to detect it, we need to have a bunch of precise waveform context to do some data analysis much quicker. So these are the current detectors. But also in the So in the future we'll have new detectors like LISA on the bottom and also Einstein telescope in Europe. So both space-based, work-based next generation detectors, and with this we will detect any sources and we will also detect joint sources like both we are working at the same time. Both in LISA and Einstein telescope. So you see like all the kind of sources you have. The long sources are the ones that we see for a long time, like spiral. So these are like massive like binaries, for example, or waves. Some of them are very high redshift, and we also have some galactic binaries. So these are the square or like over geometrical plot. And also, of course, in Einstein telescope, we see what we see nowadays, like binary black hole, binary neutron star. Maybe we can see at a bit lower frequencies, so more in the experiment. So it would be interesting. Anyway, to do with the problem, one of the main problems of this next generation of detectors is that we have many events, and we will be very sometimes will be overlapping. So we have to be able to untangle between the signal if you want to do signal detection. So that's why it also over modeling of detection. Yeah, I could have done later, but so this, you know that so this is what we see with current detector, one of the first detection, let's say. And you see that to be able to find the signal into the noise that we see, so what we directly see from the detectors, it's very difficult. It's like looking for a needle in a haystack. So I put the prediction of the matter. but I will show that something. And so to do this waveform reconstruction and to find the correct signal, it's very model. So it brings me to the second question, which is how do we do this? How do we model waves, and what technique do we use? And why do we use different modeling techniques? So again, I'm trying the detectors because we have many detectors. I didn't take a precise anyway, but there are also detecting computational waves. But you see that we have many different sources. Here you can see what like extreme exclusion spiral, comparable mass binaries, but also supernova explosion, etc. So these are systems that are very different. They are in very different regimes in terms of computational strength and velocity of the object, different frequency also, depending on the detector and the source. And so we need different tools to model this, because we cannot apply like for everything, because when we are not always in a weak regime, or we don't always have this social. And so you see that on the right, that the type of signal you can have, and you see that they are very different. Also, GR is one of the base of the baseline of this is that GR is complicated. It's very interesting, but seems simple, but it's actually very complicated. If you want to solve the equation, it's non-linear, so that's why we need numerical tools to use this non-linear things, but it's not for all ways, so we also need analytical calculation. And what is the mixture of both. And so it brings me to this plot, which shows different modeling technique depending on the system you are studying. So if you start with what is in the back, so probably a symmetric system, so a supermassive black hole on which a small object is orbiting. In that case, you have your small parameter. So the small object is orbiting, and it can go very close to the massive object, so very far. So you can say that the gravitational strength will always be weak. So that's gonna be the expansion parameter, but you can you have the small mass ratio that is very small, and this will be the small parameter. And so these are the main source for LISA, and we will see also like it won't merge immediately, so we mostly see the expert, so the small object going on. So that's why I cannot do numerical relativity, because we need to have very low. And so when you do this, at first order, the small object is following the geodesics of the big one, but then there are correction coming from the small object that is from space-time, so that's what we call cell force, gravitational cell force, and you need to have this correction up to any second order for the which there is a frequency movement. And of course, you can have different like interesting features when during the coalescence, and in particular, you have resonances, but gives you nice trajectories also. So this is one of the main techniques, and this is the huge work being done to be ready for this in particular. Then there is numerical relativity. So numerical relativity is kind of good for thing, but you solve the full Einstein equation, no approximation. So it's very nice. You can produce very nice videos, which I cannot, but okay. But the problem is that it's also computationally expensive. So it can describe only really close to the merger. Yeah, up to like, at most, I think nowadays a few hundreds of orbits before the merger. So, but it's not enough for the detectors. And so you need to overtake this. So this is the video done for the, I think the only event that was announced by O4. Like this is the merger of neutron star with an object that is around 3 minutes solar mass, and that we don't know much, we're not sure what it is. And so we did this for this object. Okay, that's it. Now let's move to the, let's say, the final method, which is what we just one, and so this one is used for So when the two objects, the two objects are still quite far. So in that case, you are in a weak gravitational field with velocity usually. In theory, you can use you can have any masses, so you can get more extreme mass ratio. But in practice, when you have extreme mass ratio, you have a lot of eccentricity, and so one of the objects got very close at some point, so the gravitational field won't be so weak, so the expansion actually will not work. So it's mostly for comparable mass, but it can, well, in principle, it's for any masses. Anyway, and so in that case, you solve, so your expansion parameter is a small v, so it's like here. It's small velocities and also small gravitational field. And so you expand your equation in this. So at first order, it's Newton order, it's just a Newton equation, and the force radiation is just what a polar emission of gravitational wave. But then you can add correction when you write on higher order, and you will have some features like tail effect and this kind of things. So correction of gravitational wave on the curvature of space-time that modifies the motion and the gravitational wave emissions. Then at first order, we solve the equation using some point particle approximations, modeling the two compact objects by point particles, just with math. But then we can add correction, and we can add in particular for different side effects like spins and tides. And so we add it on the top of the waveform we have already calculated. So the current state of the art is 4.5 ppm for point particles, both for the dynamics and the flux and the gravitational wave waveform. Then the tide has completed the next leading order, like 2 p.m. Italian effects at 5 p.m. So it's correction above this. And the same for spin. Our spin is always completed, so I will decide to do it because there are different effects. So we start at 1.5 p.m. for spin orbit, and the spin effect, so direction from spin of the object, we start at 2 p.m. and then you can make correction to this. So I think more or less the current order for the waveform is. So it's tricky, and also when you want to solve the dynamic, then it's also and to get at the waveform, it depends on the alignment between the two spins. If they are aligned, it's like quite simple to solve, but if they are not aligned, then you have position and the equation is complicated. So we more or less find it's not aligned. However, I think that it's important to the future to improve modeling of spin because what we expect. And so this is the Anders method. So it has been studied a lot, and in particular, the first way of studying was to use like what I call traditional method, which is like first solving the field equation, which comes from expanding the ancient equation with small parameter. So this is the set of Poisson-like equation, and we directly integrated them using inverse dimension function, and so this gives a solution. This is a bit more complicated, but then more recently there have been new methods and new techniques developed. So the first one is, and that came from particle physics. First one is effective field theory. Now it's so it's recent. It's a same, more or less the same idea, but like a diagrammatic approach and the integration then in Fourier space. So it's very efficient because it uses techniques and integrals that have been complicated for particle physics that we know. And it's, well, at least they claim that it's faster. In practice, it's not, I think it's comparable. But then the idea is just to use some diagram to see all the interaction and all the things you can have in your language. And integrate them with the ways of freedom. It relies on kind of hierarchy of scale between solving the physics. I will come back to this. And more very recently, there have been a new method that has been developed, which is using scattering amplitudes that were used particularly in particle physics. And in that case, they don't expand in velocity, so it can be for any velocity, but it's an expansion in gravitational field, so it's positive velocity and expansion. It's valid in two ways, the scattering amplitude is for scattering events, that's for one orbit, but then they can reconstruct the Hamiltonian and map it to Body system, get the same observer. So it's very interesting because, yeah, again, we use techniques developed for particle physics like QCD, etc. And so if we can, it's very complicated techniques, mathematical techniques, and we can solve the complicated equation and diagrams. And also, so they don't expand in velocity, so they expose the velocity terms up to some order, and so it's like orthogonal to the PN expansion. So for example, if you know the 3 PM result, it means that you will know the 2 PM result completely, but for the 3 PM result, you will miss some terms. So it can give information to some terms in the PN structure and the opposite structure. So I think in the future, that combining all these methods will be the way to go to higher.
But can I ask you, so I just wanted to know your opinion about how useful these methods, alternative ones, have been so far, the effective field theory and scattering amplitude, meaning have they been able to yield some result that the traditional PN approach has not been, or is there sort of complementarity and hope that, in fact, putting them together will give some more complete information? But at the moment, not wishful thinking, at the moment, have they been able to deliver something that the traditional PN approach has not been able to? That's my question.
So well, I think the answer is well, yes and no. So yes, because so for up to 4 PM, let's say, traditional techniques like scattering were not existing at that time, and it's different, but traditional PN effective field theory, they both got the result, let's say, more or less at the same time, a bit later. So it's a complementary. We need to do comparison between techniques, so it's fine. Then at 5 PM for the dynamics, like for a moment, I'm speaking only of the dynamics. Traditional PN is, I mean, really complicated, so I think we won't have the result with traditional techniques. And but there have been some results with both effective field theory and scattering amplitude. So I think so. I don't know if the 5 PM is complete. There have been the main result I think is the combination of methods, like what they call the tutti frutti. It means that they use result from PN, like one of these, but it's the same. I think it's because it uses a 4 PM result and what we can easily infer in PN. With method from scattering amplitude to infer the missing terms, because when we first developed, I think it was done up to 3 PM. So at 5 PM it's that, but there are some terms missing. No, it's not at 4 PM maybe. And then they used also some gravitational self-force computation, because then with this we can have terms that are leading order in the mass ratio, so we give information. So with this, I think they managed at the beginning to get results at 5 PM and 6 PM, except for a few coefficients. They have also done some results using portales at 5 PM, both in scattering amplitude effective theory. There were discrepancy between them. I don't know if it's completely solved or they are solving it. So I would say that for the dynamics, there is a way to have first results. For the first time to be the first time producing some results. I don't know if it's clear.
Not yet, but on the way to.
I think but my gut is that this is for the moment they have put most of their effort in the dynamics and they haven't produced calculation waveform, and the only way that we have produced calculation waveform is with traditional PN techniques. So they are starting to develop it in particular for effective by effective field theory, but it's not yet at the level of which we have results from traditional. For this, I think they are still a bit far. And that's a shame because okay, calculation we need first some comparison, and that's at the end what we want to observe is calculation waveform. So it's so I think they should develop it. For scattering amplitude, there are also some questions on how you map from an unknown system to a bound system, and this is not very clear. So I think when they do it and they reconstruct the Hamiltonian, that is fine. They will have the observable. But when there was some method developed by Porto to directly map to bound system from bound result, but it only works at low order. And there is no up to the point. I don't know. So it's not so useful. As always, not as useful as they probably say. Well, they always say that they can compute new things like very quickly and it's much more efficient, but at the end they encounter the same problem. So it takes time. But I like this approach. Okay, then very quickly, as you know, we need to have the full waveform at the end, and so there are different techniques. Either some smart one, taking the PM2 result, mapping it to a one-body system, effective one-body system, like small object orbiting a virtual black hole solution. Then it takes the ingredient of all different methods, even matter relativity, gravitational self force, etc. Calibrate the waveform, etc., to get a full waveform valid for any system and also for the merger and after the merger. So this is very nice, but it's a bit long to generate many waveforms. Okay, so there is another technique.
Can I ask you previous slide? What's the role of string calculation?
I have no idea.
It's a bit odd that string calculation here is helping.
Yeah, well, I think that
related to the scattering amplitude.
it's probably related. Oh, yeah, so yeah, in effective field theory, usually I think it's related to this because we start from a kind of, or at least I don't know if it's this, but for the matter, we start with like non-to action, and then we use like branch multiplier to map it to a point particular action. Corrections probably
Techniques for string calculation.
but well, probably they put all everything, but it's but they use it. And then you have like more direct class of waveform, like that one that just takes the PN waveform that is valid up to some point, and then they add their waveforms on unknown parameters to extend a bit. So first unknown PN parameters to describe the incompleteness of the parameter. So if you had like 5 or 6 PN parameters that are not known, but they can determine them, and then we have a phase of intermediate phase before the merger, then the merger phase, parameterize each one by some coefficient. Then we take a few numerical simulations. We don't need too many, and then we can use them to calibrate their waveform and to give some parameters for some value for their parameters. And doing so, they have a full waveform. We can apply it to any kind of the system, like any masses, and in the model for speaking star. And so once they calibrate it with numerical waveform, they don't need them anymore, so they can generate the waveform very quickly. So this is very nice because they can. So that's why we got a class of full waveform. And so that's it for the modeling part. And now I just want to say why do we want to go beyond GR? And I think it's so the first thing is that going beyond GR and trying to modify GR, it also tells us a lot of things on how GR works and why does it work so well and why is it so complicated to go beyond GR and to have a system theory that gives good solution that behaves correctly beyond GR, while for GR everything works well. So I think it's one of the motivation. The other one is of course that we have still even though GR is working very well, especially where we have tested it, but we have some inconsistencies. So we have the physics, we have variety of cosmology for like people have spoken about it recently with this pixel, but to explain dark energy, dark matter, etc. We can modify gravity, but of course when we do it, we can do it in many different ways depending on what you want to test. You can add additional things, go to gravity. Break some assumption of GR, go to Taylor dimension, local theory, bioelectronics invariance, etc. I have curvature, so and so you end up with many theories, and you cannot do anything with it because we have too many theories. So you can, at the end, people are just picking their framework theory and try to study it and to get some solution for it. But well, it's nice. People, I think it's good that people try to build more framework theory. It's always good. And so the last thing, they help you to be able to do some tests on gravity. And so on the top, you have some test constraints on some theories, probably on a Jordan theory, like the Jordan sticky theory. And so this is done with triple pulsars. And it's a way to follow the theories of theory. So I think currently most of the best tests are with pulsars. And then at the bottom, you have the test of done by Lego and Virgo, and these are just agnostic tests. We don't consider particular theory, we just take the GR waveform, we modify it as a post-Newtonian parameter one by one, and they constrain this the modification of each PN parameters. And so obviously, we find good agreement with GR, so no deviation. You can see that the best constraint is for the depolarization because we don't have it in GR, so that's very easier to constrain.
What we can see for a bunch of events.
So this one is for the, so it's 21, so I think it's with combining all events that they had at that time. I think it's for 2 maybe. So they could stack but still it's not the best. I couldn't find a similar result for all 3. Although I think it should be better. But it's good, but okay, you can see that it's just like considering the parameter one by one and also do something. So yes, so well, I have answered my 3 questions. So I could stop here. But I can also go to what I want to say. So the main question I want to answer now is, okay, I am doing some tests, but let's suppose that I have a detection by, for example, with the previous test with Lego and Virgo. It's agnostic test, it gives me that I have a detection, but well, what can I infer about it? Can I go back, trace it back to some specific theory or to some kind of deformation of the theory that I could have? So this is, I want to give a way to answer. So the first remark I want to do is that we have this test, very nice, but we have some inconsistency. We also, my slide in order, we also have some specific tests. Well, I don't know if we are doing this test, but at least there have been a lot of work recently, both in analytical method like PN and in numerical relative to have full waveforms beyond GR to be able to like run the data analysis machine with also alternative waveforms, and so it has been done mostly in scalar tensor type of theories. And like I have replaced the main result, like it's more or less VPN, which is okay for the accuracy that of the current detectors. We have also using times up to a higher order. And there have been results in for the type of theories that can be performed on the previous result for single scalar tensor. Because if you go, for example, for instant scalar bosonics, the bosonic term that you add, it just gives the leading order function start at 3 p.m. And so it's almost the accuracy we already have with scalar tensor. For many, the two it's okay. And for assignments, it's also we have limitation on the leading order scheme, because that's what is most interesting for chain segments. Solutions are different from the for spinning black holes. Anyway, but all this is still at the beginning, and of course we cannot do full waveform for all the theory that we have, because it's too much more just for one theory. So if we want to complete all theories, it won't be possible. So we need a way to still do agnostic state searches, but as I said, the agnostic searches are limited because we can miss some deviation. It doesn't take into account the fact that the PL parameters, for example, are related links. You cannot just modify one and assume that the other will be modified by this modification. But I mean, studies that show that even if they modify the waveform at some PN order, by running the analysis with some, they found a deviation at a different PN order. So it's correlated. So it doesn't work like this. And also, for example, you can miss an effect. Suppose that I will show you have a theory for which the deviation starts at a higher PN order, then you won't see anything because you are only searching it, but you don't have it. So of course it will be modified at that point. And okay, for like going general, it's all what we can do, but for next generation we want to have the sensitivity. And also, as I said, we don't have a systematic way to connect deviation to the new parameter. So my goal is to have a dictionary that tells you if you detect this deviation, then you can assume that this will come from this theory or this kind of thing. And so to do this, I will use what has been called as the effective theory of gravity, which is considering theory by modification of GR by adding higher curvature fraction. And so it's an effective theory that you can stop at some curvature, the curvature of some mass scales, and you can stop at some mass scale to see the deviation. So in practice, so the reaction is this one. So you have GR, and then you have the curvature correction. So it starts at cubic curvature because the quadratic it's not mentioned. It's a surface time. So it doesn't give you any theory, I think. So in this, it comes with some parameter here. I've written it so that the parameter is dimensionless. So that's why you have the mass scale here at value. And so this is the mass at which the new physics appear. And then you have what I call my new higher curvature term. And so it's of order P in the Riemann tensor. So for example, our three is three products of the Riemann tensor. So for example, for cubic gravity, all the terms you can write are given here. Where you can construct the tensor differently, and you can also have some like different parity terms by adding so that in practice, so this is the simple theory because we have no curvature, but in practice you can add some additional derivatives acting on the Riemann tensor, for example, and you can also add some scalar field to it. I suppose that the function of scalar field in front of it, you can also have derivatives on this scalar field. And so my goal would be to take this theory, or the one with all the possible terms, derivative, etc., and to tell you at which order, what would be the leading order of contribution to the dynamics and the wave.
Why disregard, say, Ricci tensor?
Because Ricci tensor can be replaced by, you can use the field equation, so it will give you one input.
In all?
Yes. Well, if I think if you use with the symmetries of the Riemann, well, it's still something we are discussing. So, but in principle, like when you write all the possible terms, for example, for cubic duality, you would have also Riemann tensors, pretty tensor, scalar, etc. But first, you can use the symmetry of the Riemann tensor to write them yeah, you can manipulate it to reduce it to a certain number of tensor, and also you can use the field equation as a order. So your field equation will be something like mu equal to alpha by alpha something. So if you plug it in the field equation, then it will be something that will be square of this, and so you can reduce your order and it will calculate order.
You're saying that lowest order you will have on the right hand side any regions.
Yeah.
You could do this order by order.
Yes, but I think, well, up to now, people have claimed that by doing this, using the field equation and but because also, yeah, well, I've claimed that if you write all the possible terms, you will have many terms, but then all the terms that you use, which is scalar and which tensor, can be revised as a function of the Riemann of these terms, or can be removed because of the field equation. Actually, we are not completely sure of this, to be honest with you. But it's something we don't understand completely, so we just what it was. So consider this term here. So this is a cubic duality term. So in principle, the argument I told you is fine. And then there are two things. So first, again, so this, if you do a field redefinition, then you can make it disappear from the action. So you modify your metric by something symmetric. Something like this.
That's also in front of the.
Yeah. It's symmetrically. So if you do this in the action, this term will disappear. Because this will give you from the rich scalar will give you r times k, and then it will disappear or add higher order. But there is a problem that so if you do this, then suppose that you had only this term in the action, then you do the field redefinition, then you have the solution for your gear. So if you solve for your new metric in the action, this you will have suggest some gear solution. So no link to your new physics scale, it will be short. But then if I don't do this, or if I consider my theory and I do my I see the difference and I don't find the So it's not completely clear that you can disregard them completely. In theory, doing this is good, but it's I can tell you more later.
There's also a bunch of identity for dimensions that come from the other densities.
Yeah.
Where this is used to some extent translate Ricci scalars and Ricci tensors into.
Yeah, but that's what is used to reduce to this. we do this, but there is still sometimes, I think that this time of this, but
I wasn't sure if this could be done completely fast.
yeah, I don't think it can be done completely. There are still some more them. And it's, yeah, well, it's more or less the same as the code monitor for the environment that I want to environments, and so you reduce the number of them. Yeah. And so my goal is to determine what is the waveform for this theory, particular theory I have. So I remember that I have my main ingredient new parameter is this mass scale, and I want to determine the scaling of the waveform with respect to this mass scale, and also at which PN order is equivalent. And so it won't be the same. So I want to determine this Q and this M, and because if I have this, then I can suppose that I have many elements, then the scaling will be different. Like, for example, will appear at the same in order, but different scaling in mass. And so here on the denominator, you have mass of typical mass of the system. And so if you suppose that I detect like system with different masses, you can do some statistical analysis to disentangle from systematic bias that I have in my experiment. So this is a way to detect it. One of the main results, if I have this, is that you see that I expect to see a stronger deviation for low mass system, because like large mass system have a curvature that will be weaker near the horizon, so there won't be, and I'm considering a theory for higher curvature, so then they will be more reduced. So that's why it's low mass system, so it's system that we see in like one general trend, and that we will see in the Chinese scope. And also it will be stronger in the spiral. Because I'm considering also low mass system. And so yeah, the goal of the following is to determine these two order coefficient Q and N that depends on the so P, which is the order of the curvature. And to start, yeah, well, I will not use traditional PN, but I will use effective filter extension because it's well, it's nice and it's a order contribution, and it's again considering already a effective probability, so it makes sense. But still, it's a perturbative, so small perturbation. So just to give you a bit more detail on the algorithm, it relies on the hierarchy of scales. You solve scale at different scales your system, and you start by solving the internal system. So this is what is at the bottom here. So your individual objects, and you solve in your theory. So then the small scale is the orbital scale, so the dynamics of the two objects. And finally, you solve the waveform, so the Broadcast wave. And thanks to these very different scales, you can integrate out the previous scale in your system to get the dynamics form. For example, to get the internal motion, the partial approximation, it's actually I will also just because I will mostly speak about the scalar field side, so I use so I will perturb my metric, and I use what we call the Boltzmann decomposition. So it's a scalar vector tensor decomposition of the metric, and in particular, as I will look only at the leading order equation, I will consider only the scalar field equation, because the vector one and the tensor one usually will come with velocity. Will be contracted with velocity in the PN expansion. So let's start with the inner region. So as you know, we have to make out internal degrees of freedom. So we have one particle effective in theory, and it's mostly the point particle approximation. So just mass. And so then if I do, for example, introduce in this section, so my decomposition of the metric in terms of phi, A, and sigma, then I will get the let's say, followed by linear order, the action, the point particle action. In particular, I will have the coupling between the mass and the scalar field, the gravitational degree of freedom, and I will use, and it will give you my, if I want to use the diagrammatic approach, it will give you what I call the matter gravity vertex. So my straight line here is with the one called model one particle, and this one model the scalar field, the dash line. And so this, when I have this, it means that I have an interaction between the mass and the scalar field. And so it comes from this term here. And so it gives you all this, in my diagram, all this vertex will behave, and it will give a contribution like this. But it's directly extended from this. Of course, at higher order, then I can have the mass, and I can have different, even this, I can have different higher order interaction with more than one field. And then from so just, but it's just, you can read it from developing the particular action.
That one would be phi squared?
Yeah, this will be a phi squared. And of course, you can have, for example, you could have this with phi, and let's say this is A, and this is particle, this is phi, so this is a phi A squared. But as I have A, usually it will come with a velocity. Here we have the velocity. So this is for the point particle, and of course, afterwards, if you want to beyond the point particle approximation, you can use finite size effects, which are tight. We make use of this, like the electric type of phasal effect and magnetic type of phasal effect, etc. And you can also add the spin. Spin is always more complicated. In that case, the action is given by this, and you have to introduce some spin tensor. But that gives you too many degrees of freedom, so that you have to keep them where it's the whole machinery and spin are complicated to use and not complex.
How do you decide this would be better?
So the most used is this one, but there are a lot of discussion on this, and people have studied what changes. I don't really know. I think recently there have been a paper on by people from scattering amplitude. So they have the same problem, and they say that okay, we assume that we don't impose any supplementary condition, and we look what happens in the spectrum. And they claim to have more, so the new degrees of freedom, but we have additional degrees of freedom. I think they are saying that they have some physical effect. So I still need to understand better what they are doing. I find it interesting because then they don't have this kind of ambiguity of yeah, so that's it for the vision. And the near zone, so I just give you, just to point to understand the two diagrams that I will show, I give you. So when you do the same, but with the bulk action, so just the Ricci scalar, you do your decomposition, you expand, and then first you will have some quadratic actions, like it's simple, it's quadratic scalar field, it's d-phi, and the same for the vector or the tensor, and it defines you the propagator, because if you vary this, it will give you just box I equal to something, and this phi is propagator. So it gives you just like each internal line that comes either for the scalar field with some momentum, for the vector, or for the sigma, the tensor part of the decomposition, then it gives a propagator like this. So in practice, it gives exactly this. You need to integrate over the internal momentum, and then it's one contest. So this is just the inverse green function. And then if you go to higher order, you have pre-cubic order. So here for GR, I kept only the one that introduced with only the scalar field. And if you see it in GR, so from the Ricci scalar, you only have time derivative. So it means that it will give like something like this for the cubic vertex, interaction between three scalar field. And in particular, as it's only with time derivative, it's only the zero component of the momentum, and the zero component of the momentum, or the analysis of freedom, comes with a factor b. So it's a v-square, so this will be reduced with the non-contributor. I forgot to mention the important thing is that when you go to but on this expansion is you go to Fourier space and you have this hierarchy of scale. And so in particular, if you are in the near zone, your internal vertex will be off shape. So you don't have to swap it. And so you can determine the scaling of this wave vector. And so my vector will be like this. The zero component and the vector 1. And for off shell, it will behave as 0 or more. So this is okay 0 and only 1 or. So that's why you can do post-linear expansion because you have then that k0 is much smaller than k. And so in particular, if you in your integral in practice you have the full k when you integrate, but then you can divide it as 1 over like something, and so then you can do post-linear. When you will describe the radiation, all things that are not internal but that goes infinity but are the what is radiated. So this is the K potentials for the internal one. And then for the radiation, they are off shell because they are limited. So we have to make it specified. And in that case, it will be like this. So it means that for this type of K, we belong to the K expansion, but at the same time, we are reduced with respect to the K factor. Anyway, these are things, but it's to explain why you have this behavior. And so so you see, I've seen I gave the scaling also for each short distance to know exactly at which order, like if you don't want to get the exact number, but just knowing which order the diagram contributes, that's the way. And so if you do this, you can go back to your like higher cubic gravity, and in particular, for example, I do some specific cubic gravity equation. And in that case, it will you have a new vertex that will appear because you have new interaction. And if you look at this, in that case, the leading scaling is d square 5, 8.5. So it gives you this action at cubic order. And so it defines how the cubic vertex from cubic gravity will come from. And in particular, it will give something like this, and you have the scaling that will depend on the plane and the radius distance. Yeah, and so thanks to this, once you have determined all this, you can just directly get the leading direction. And so for the radiation, you have this with diagram. So you have like coupling with mass and the scalar field, and the same for the two objects and the cubic gravity vertex. And so if you put everything and solve the integral, I think the exact result for the potential, the binding potential equation with G1 is this. So I introduce here the coefficient constant for you to see the term. So the first term here is just the Newtonian potential, and the rest will be the correction. So the first term you see is scale, it looks like 1 pm correction. But then if you introduce the exact mass scaling that you have here, etc., you will see that it gives an additional 4 pm correction. And so at the end, this will be a 5 pm. So what I'm saying is that for cubic gravity, the leading contribution is 5 pm. Then you can do the same for follow moments. So when you emit a graviton to get the waveform, and so this is a diagram like this. You also have a cubic vertex because that's where you see different for cubic gravity, but with an emitted, so an on-shell. This one will be on-shell, the other one will be off-shell. And so the scaling will be the same. It will be 5 pm. And so that's my. So it means that so this will give exactly the scaling of the waveform I was expecting. show you one. Well, I don't think I will speak much about this. So you can 5 p.m. It's you like in GR. If you work quickly, 5 p.m. is also starting. And so in this theory, in principle, you can have the GR. You have the GR term, so you will have the GR final effects. So GR for black holes are high, so it's not interesting. But in this theory, in principle, you have different black hole solutions. In particular, this black hole solution will have could at least have log numbers that are non-zero even for black holes. In particular, as we know that for GR they are zero, we know that the new log number will scale as your cookie, proportionally to your cookie. So this is something to be taken into account. But then, so if you do the modelization of tidal effect in GR, you have this just from the Ricci term already. You will have tidal correction that will come with the log number. So this will be just the GR correction. So it doesn't need for example to have the 2D vertex, it just needs to have tidal with the matter. And in that case, it will be proportional to V over 6 over 5 because it's a 5 correction in GR, we know this, and with the log number, the new log number that will scale proportionally to my cooking parameter, the new physics scale. And so you see that it's also 5 pm. So in cubic gravity, you have two contributions at 5 pm, the one coming from the new physics term, so particle, and the tidal one. If you go to higher curvature, then you will have the same, you will still have this, and you have 5 pm. But then the other term will enter at a higher. That's why I arrived at my evaluation. And at the general case, so suppose I have any higher property term, then I got the result. So this is for the generic case. This is the result. So you have the potential, the binding potential, the generic one from the new vertex. So you see you have some plane order plus some scaling in the mass. You have the result for the waveform usually is the same. And additionally, you have the tidal term that is always at 5 pm, but with the different by scale. And on the right, I'm putting the example of cubic order that I just mentioned before, and also of quartic. So when you have 4 answers, so in that case, the diagram of the 4 vertex interaction. Okay. Well, and you see that in that case, so the main one, you think it will start at 8 p.m. So 8 p.m. But in practice, you need to take into account that you also with tidal term that is starting back. And so then I have, so this is my main result. And what you can remember is that we have determined the leading correction for most. For higher probability, it will always be 5 p.m. But only for if you have tidal, like low number. So I gave one thing is that I gave the expectation for such term. In practice, when you do computation for some terms, you will have cancellation because of the tensorial structure of the term you're considering. So this I didn't take into account. For cubic quality, for example, in the 3 terms I've given, one of them is 0 at 5 p.m. So the first contribution will be 6. And the other one, the one with the epsilon, because of the epsilon, the symmetry, you need to come with the velocity term, so it will be 5.5. So I don't take into account this, I'm just saying that the leading fraction will be at this. Then you can also do the same adding the scalar tidal effects, and in that case, you can determine the same PN order and the new physics order, scaling on the mass. You need to take into account also that when you scalar tidal effects, you start at 3 PN, so this will be the leading correction. And that's it. And just what I will say is that so this gives you a systematic way to distinguish between new physics and systematics, because then, as I said, you can do some statistical analysis because you have the mass scaling, and so this will scale differently for different mass. And also this can directly be integrated into the current test strategy in and then go back to which kind of theory, let's say, which kind of new physics you are after. That's it, thank you. And at the end, I promised you that you can find the leader. So I'll let you look at it a few moments, and then again.
Yes. So this dictionary was calculated using the framework of effective field theory, and there is only one there is only a region in the parameter space for which this approach is applicable. So, so my question is what happens in the other regions?
Yeah, well, we don't know what happens in the region, but we are limited to the expected to arrive at like high energy. And so we in the system we are considering we are like way beyond this energy state, so we are fine.
But so these effects of in physics are not expected to appear at the other regime where this is not valid.
No. Well, yeah, no, it's a way to so it's like you are to it appears that I but we are not reaching. But we want to have a regime where we see differences, but not where it was two points.
So I have another question, but so could you please go back to the plot? I think it was by Carvalho where it says where it shows the different methods that are used in different regimes. I think it was close to the beginning. That one. So so what happens in the if we happen to observe something that is in the gap between different modeling
So
techniques?
it's always so before I go because here that's it's a pretty plot which takes some specificity, but I think eccentricity also. But anyway, for example, it has been shown that gravitational self force it's working very well actually beyond the extreme association scale. So even at for a ratio of 1/5 system, it works very well. And they are also it waveform of 1/10, and it's not so bad.
I see.
So in practice, there
overlaps.
is not this huge gap. And it's the same. So before in some plots they were separating positional and numerical, but now it was fiction, but there is some intersection and overlap. So yeah, I think that there is overlap between more or less all the method, and people are doing comparison between techniques.
And how good is in these regions where so how good are the methods? How good are the predictions? Like in percent in this region where these that are shown as gaps here. So are both methods equally as good or not good?
For example, so I know that so they compared waveform from numerical relativity at 1/100 and 1/10, and I think the bottom line was that 1/100 was very good. So the agreement between the two were very good. And when we do this, I think we're sure that numerical relativity is quite fun. Because it's okay. And this, I don't have the number, but that's they were saying that even for 1/10, frequency was not very high.
And so wait, maybe just a question more. So in I see that there is the regions that can be modeled with numerical relativity also ends in the axis that separates circular from scattering. So what is the main problem there? Is it because others I understand not from equal to asymmetric, maybe it is the resolution, not you need a lot of resolution.
Yeah,
But in that case, I see, because maybe you have to start the binary from very far away.
Yeah.
I see.
But on the eccentricity, it's also complicated to compare things because, well, now, because eccentricity is not defined the same way, it's different with different techniques. So it makes it more complicated. And also it is, probably it hasn't been studied much, but it is assumed that when you have a binary system, especially for natural worlds, after many orbits start to circularize. And so when it enters into the region where the natural relativity is valid, then it has always circularized. That's why we take initial conditions that are almost circular.
I see. Thank you.
Other questions on Zoom? So, more questions here in the room? Yes.
Can I ask another one? I was curious. So this concept of the dictionary is, of course, very nice, interesting, and important. I would say. I mean, if you have some kind of agnostic approach, abbreviations, how do you map, right? And but of course, here you use a particular class of theories, these effective models, and in that case, there's this kind of certainly small number of parameters more or less in control. But how do you envisage the more challenging question, which is, within the broader space of theories, how do you map any deviation?
Well, I think the approach I've taken, it can be, because like the parameter are the one you introduce when you set your, so in our case, we introduce it, it's just linked to the other. Well, we even have different parameters.
Yeah, like a max parameter or whatever, yeah.
And I said already that I can add the scalar field and derivative of scalar field, and it won't be a problem. We can do the calculation and we'll have the results. So for the scalar field, so then it can compose all the honestly. When I write my theory, I don't ask myself the question of is it valid? Because of course there are some inconsistencies in all this. So this I just want to see what would be the way from so then it can, in principle, it can also be done for if you had vector people. I don't see the problem. And so in that case, you can also, like, even if you have a complicated theory with different parameters, but the vector field, then you can still map this down. My question is if you have relevant violating theories that are a bit more complicated, so place I have the answer.
That's an extra one. But even just looking at the mass dimension, which is the of your expansion mass dimension of color. Right?
Yeah.
So if you keep on adding effects, then you have more parameters. And then there's of course questions about JLC and all of that.
What do you mean by adding more?
Okay, so if I assume that not only I have curvature terms, but I can have other things, more complicated interactions. So say at what you call cubic order, then instead of having just the terms that come from gravity, I have a bunch of other terms that comes from interactions or a bunch of other fields. And that could
so for example, at the same mass order but with a scalar field, derivative on it,
a vector field, other tensor fields.
Yeah. But I think we are studying two things: the post-Newtonian order and the new physics mass. Okay. And this, I don't think they will be the same. So well, I would have to check. use it. But for example, just like scalar field and payment. I don't think so. The order, like, you have the PN order, and then you have the mass. And depending on, I don't think, so probably that if you have a term with like, I think this and this give the same mass scaling. This is like M3. Same number of derivatives.
Yes, there's the number of derivatives it is.
So it's the same mass scaling, my scalar.
There's no dimensions in your counting yet.
So I think the Q will be the same, but the PN parameter won't be the same.
Right.
And I think it would be a way to disentangle. But that's true that
But kind of self-interaction. And there's a couple. For instance, if I put just m squared times 5 squared, then the mass brings in a mass dimension, which is like the derivative. And then if I put 5 to the 4, 5 to the 6, then there's a coupling which is dimension 4. But you're saying that perhaps the velocity order could break the degeneracy. That's what you're saying. Well, that could be nice.
Yeah, well, yeah. We haven't considered mass. Also because
Because, for instance, when people were looking at the scalar Gaussian models that you introduced, so you can have different couplings, like 5 squared times Gaussian.
Yeah.
And then people put, oh, well, not 5 squared, but exponential of 5 squared. But the exponential of 5 squared has 1 plus 5 squared plus 5 to 1. So all of these.
This we cannot, yeah.
Right, and then some other people said, but this doesn't make any sense because you're neglecting just corrections in the scalar that appear at the same mass dimension.
Yeah.
Because you could have then self-interactions without coupling actually to gravity. Anyway, so
Yeah,
this
yeah.
problem
So
has been
that's
established.
the thing. So like here, I for example, the power of the scalar field, but in practice, if I do the expansion, it's computing only the leading order that will give the first equation. If I have a like I'm doing a PN expansion, so I actually it's 1 plus delta psi. So if I do this, I have this, and so this is the one PN, so it's 1 over this. Then I just do this. Plus something times. So this will be I obtain order. So if I look only at the first order, I cannot tell you the difference between different like it will be different reason because this is the power and the here will matter to the equation, but if I just look at the scaling of the leading order, so yeah, that I cannot go back to the precise original theory, but I can at least tell you the family of the two, or the correct number of derivatives.
Right, I think it's kind of mass dimension of the corrections.
It's well,
Yeah.
derivative is directly. Yeah, well, I hope to check, but maybe I can tell you if you have additional derivatives. Also, because when you are starting, when you start,
But if it's mass, you know that.
yeah.
But
Okay, so I think we can stop here. Thank you again, Laurent.